Hi, good morning. This is going to be the third chapter on the exam. And in this one, we are going to study electric currents. And we are going to use like three equations. I'm going to go over all this stuff in here. This is one. And the second one, it is this one. And the third one, it is this one, okay? And mainly my lecture today is gonna focus into these three with problem solving. Just before I start, I wanna share with you this video, which is a YouTube.
Graduates of Harvard and MIT, the Massachusetts Institute of Technology.
We are the premier engineering and science institution in the world.
Do you think you could light a bulb with a battery and wire? Do you think you could light a bulb with a battery and wire?
Yeah.
Light a bulb with a battery and a wire. Maybe. Yes.
Right.
Definitely.
Do you think you can light a bulb with a battery and a wire?
Battery and wire? Well, yes, why not?
Okay.
Definitely.
Okay, can you do that?
The interesting part about the batteries and bulbs question is that people always predict that they can do it. Students say, of course I can do this.
Any hints I should have here?
Teachers say, of course my students can do this.
Ow! Do you know why that didn't work?
I have no idea.
Battery could be dead, the bulb could be bad, I'm hooking it up totally incorrectly. I'm not an electrical engineer, I'm a mechanical engineer. But if I had to guess, I would say it's operator error.
Okay.
I know it's possible, but I don't know how to do it.
It's only after failing that you begin to get upset with the question and think, well, maybe it's a trick question, maybe this has something to do with manipulating the wires. They couldn't hold all the wires together.
You don't have a current if you only have one wire, you need to complete a closed circuit.
But that's not the case.
Oh, well, if I do it with a little light bulb, I just do this. In which case, the light just lights up.
It goes to the fundamental understanding of electricity. If one cannot light a light bulb with a battery and wire,
All right, then now we are going to go to the understanding of, the basic understanding of electricity and electric current, electric circuits. And maybe most of the students in the video, they were like thinking, okay, I have that kind of circuit. Okay, then it's broken here, nothing in here. Then I will not be able to to do it. But the thing is, the student who was able to do it, he understood that there are two, let's say, terminals for the bulb. One of them is the one here, and one of them is here, and then I can use the same, let's say, wire. This is the wire, and this is the battery. In a way, like, okay, what he did is actually this. Okay, in like an actual picture, like the battery was here, right? And then he connects that wire here. Then this is like with this is the circuit. Now we are going to see that we are going to study circuits in general, and these here are they gonna be like in this chapter, they are going to be simple circuits. And also they're gonna be now DC. DC means direct current. It's the current that is gonna keep its magnitude and direction for the whole life of the battery. I represent the battery with these two here, one short, one long resistor. I have it like this. This is a switch, and and actually what's happening is that electrons, they're gonna leave. This is the actual current. It's gonna be from negative to positive, or we call it the electronic current, which represents the motion of electrons. But the conventional current is going to be the one that we are going to use in all our circuits, is going to be from positive to negative. Now we will use for the electric current I. And inside a wire, we're going to find that electrons, they're going to cross a certain, this is like area in the wire, then this is really a certain area, and the electrons, they're gonna cross that area. And as if I'm gonna count like how many electrons are going to go through this. The first definition for calculating the current, it is charge per unit area, and that means you divide the charge by the total charge by time, and therefore I can define the unit for current to be coulombs per second, which is amperes, and ampere, it is a standard unit, the standard unit for current, and this is one of the basic SI units in the in the SI system. Now remember the charge, we did that in the previous chapter. We said any charge is gonna be a multiple of the electronic charge, and here N can be 1 or 2 or 3 or 4, because remember the smallest charge that we have in nature, it's the electronic charge, and then I might have 2 of that, 3 of that, 4 of that, positive or negative. Then delta Q, it is that number of electrons multiplied by the electronic charge, which is 1.60 10 to the negative 19 coulombs. Now the actual motion of electrons inside a conductor, it is completely random. Then they are drifting in all the directions, but I can make them directed or having a certain direction. All of them is gonna be aligned with having a potential. We call this here potential difference, which means I'm gonna make one of them negative and one of them positive. This is the positive, this is the negative. Potential difference is equivalent to the word that we are usually using and called voltage, and it is measured in volts. Now, of course, that velocity, we said we're gonna call it drift velocity, and we can prove that the current equals lowercase n times Q times A times V drift. Remember here, we are going to use uppercase V for volume and lowercase for speed. Now I here, it is the electric current in amperes, and it is the number of free charges per unit volume, because I'm saying if like free charges because I'm talking in general, I'm not only talking about metals. And then lowercase n is gonna be uppercase n divided by volume, where V is the volume.